August 1944, Augsburg, Germany. The smell of oil and fear hung in the air as sirens wailed over the Heinkel aircraft works. The Allied bombers were closer every week, and the Luftwaffe's miracle weapon, the jet, was still a fragile promise. In a dim hangar lined with half-finished fuselages, a quiet physicist named Hans von Ohain, age 33, wiped soot from his glasses. Around him, the sound of metal hammers echoed like artillery. Every man there knew the truth no officer dared to say aloud. The war was being lost, one failed engine test at a time. Before we continue, if you love discovering hidden wartime innovations that changed history, hit subscribe. Now back to the frantic testing inside the Heinkel hangars. Von Ohain was not a soldier. He was a physicist who believed in air. Not the air of speeches and slogans, but the invisible, measurable substance that could lift a machine if handled correctly. He had joined Ernst Heinkel's aircraft company in the 1930s, long before Germany's generals realized what his theories meant. He had already built the He-178, the world's first jet aircraft, in 1939, an elegant proof of concept that had impressed no one in power. In 1944, that same lack of faith haunted him again. The Luftwaffe demanded production, not theory. Every engineer was told, build what works, not what might. Yet what worked was failing. The Messerschmitt, Me-262, the pride of German aviation, was fast nearly 870 kilometers per hour, 540 mph, but dangerously unstable. Its straight wings, designed before engineers fully understood high-speed aerodynamics, became unpredictable near the speed of sound. Pilots called it Die Schlange, the snake, for the way it bucked and dove without warning. Compressibility effects. The buildup of shock waves around the wing as speed approached Mach 1 made the aircraft pitch violently nose down. This phenomenon, later called Mach tuck, killed more test pilots than enemy fighters. Von Ohain understood that the Me-262's problem wasn't just its engines, it was the air itself. At those speeds, air didn't behave as a fluid, it compressed like a spring. The wings bit into it unevenly, creating pressure spikes that pulled the aircraft downward. Engineers tried thicker metal, larger control surfaces, even rebalancing the center of gravity. Nothing worked. The Reich Air Ministry, desperate to field jets before the Allies did, ignored the deeper problem. Inside Heinkel's offices, von Ohain proposed something heretical: sweeping the wings backward. Instead of meeting the air head-on, they would slice through it at an angle 35 degrees from the fuselage line. This, he argued, would delay the point where shock waves formed, allowing faster, smoother flight. The mathematics supported it. The aerodynamics textbooks did not. His peers dismissed it as academic nonsense. One senior designer told him flatly, "Wings are meant to lift, not to run away from the wind." But von Ohain had data. At the Göttingen Aerodynamics Institute, experimental wind tunnels had recently shown that a swept wing reduced drag at high subsonic speeds by as much as 20%. The airflow met less direct resistance, spreading pressure peaks along the span instead of concentrating them at the leading edge. The concept had appeared briefly in pre-war British journals, but no one had pursued it. Von Ohain saw potential where others saw risk. Still, no factory wanted to build an unproven design. Metal was rationed. Fuel was scarce. Each kilogram of aluminum was worth a rifle. Heinkel himself, an innovator but also a realist, hesitated. He told von Ohain, "We build for the Reich, not for theory." The order from Berlin was clear: produce me 262s, not prototypes. Yet von Ohain continued sketching in secret, using the backs of requisition forms and scrap engine panels. He called his concept Project 1072A High Speed, swept-wing jet built around the new He-S-0111 turbojet, the most advanced engine Germany had yet developed. The environment around him was collapsing. Allied bombing raids leveled supply lines weekly. The Mariennahe test site near Rostock had been hit twice. Engineers worked at night under blackout curtains, the only light coming from oil lamps flickering across blueprints. Fuel shortages forced the cancellation of nearly all flight trials. In this atmosphere of desperation, Innovation was not encouraged, it was punished. Deviating from orders could mean dismissal or worse. Still, von Ohain and a handful of technicians persisted. They tested small wooden wing models, blown with compressed air through improvised ducts to mimic high-speed flow. They recorded the angles where airflow separated and compared them to existing Mi-262 wings. Even under crude conditions, the results were clear. A 35-degree sweep delayed compressibility effects by nearly 10%. The discovery was quietly extraordinary. But in 1944 Germany, quiet discoveries didn't save funding. At Luftwaffe headquarters, reports of the Mi-262's instability grew urgent. Some pilots refused to fly it in poor weather. Commanders demanded modifications, stronger landing gear, larger stabilizers, but never questioned the core aerodynamics. Official doctrine insisted that straight wings were safer, easier to manufacture, and more predictable. Swept wings, they argued, belonged in university drawings, not in warplanes. Von Ohain knew that to prove them wrong, he would have to build one himself. He convinced Heinkel to allocate leftover materials from damaged airframes to assemble a small-scale prototype. It would not be armed, and it would never see combat, but it would fly. In August 1944, the first parts were laid out under the codename P-72. Heinkel's senior staff called it Das verrückte Ding, the crazy thing. Each evening, as bombers rumbled over the Baltic coast, von Ohain stayed behind after the all-clear siren. He checked stress diagrams and airflow plots drawn by hand. His calculations showed that the new wing could reach 950 kilometers per hour, 590 meters, without structural failure. But there was no time to verify. The Reich's industrial collapse left only fragments of opportunity. Every day the front lines moved closer. Every night the orders from Berlin grew more erratic. By the end of August, as the Allies crossed the Seine and the Red Army approached East Prussia, the Heinkel engineers faced a decision: shut down all non-essential projects or hide them. Von Ohain's prototype was moved to a storage hangar, its swept wings half covered in tarpaulin. To the casual eye, it looked like another unfinished jet. To those who knew, it represented the final step toward a new kind of flight. No one in that hangar could have imagined that their unfinished machine would shape the next century of aviation. What they saw as a desperate experiment, the world would later recognize as the first glimpse of the transonic age. What no one expected was that one man's impossible idea would work. The innovation began months earlier, born out of frustration and necessity. By late 1943, the Luftwaffe's jet program was choking on its own ambition. The Mi-262 could outpace any Allied fighter, but only in theory. In practice, its airframe trembled at high speed. Its control surfaces stiffened, and its pilots feared the invisible wall that came before sound itself. The engineers blamed everything except the air. For Hans von Ohain, the answer was not in bigger engines or stronger alloys. It was in how the wings met the wind. Von Ohain's obsession started inside the aerodynamics lab at Göttingen University, where he had once studied fluid mechanics under the pioneers of modern flight. There, in 1935, he had first glimpsed a test curve that defied accepted theory. When a model wing was angled backward by 30 degrees, the shockwave that caused drag shifted outward, delaying compressibility. Most researchers dismissed it as a wind tunnel artifact, but Ohain remembered it. 8 years later, as Mi-262s continued to suffer from control loss above 500 miles per hour, 800 km/h, that forgotten chart returned to his mind like an unanswered question. He began sketching ideas on whatever materials he could find: cardboard, packing paper, even the steel skin of dismantled engine nacelles. With a grease pencil, he drew backward swept lines at precise angles throughout 35 degrees 40 each one, a hypothesis. He reasoned that by redirecting airflow diagonally across the wingspan, he could reduce the abrupt drag rise that crippled straight-wing jets. The wing would, in effect, trick the air into thinking the plane was flying slower than it actually was. It was an elegant solution to a brutal problem. At the Heinkel Aircraft Works in Rostock-Marienähe, von Ohain assembled a small group of technicians, 5 men, who trusted mathematics more than orders. They scavenged materials from scrapped aircraft, aluminum ribs, wooden spars, and the remnants of bomb-damaged gliders. With these, they built a makeshift model roughly 2 meters wide. They called it Der Vogel, the bird. Its smooth, swept wings looked alien among the angular, pragmatic lines of conventional fighters. They lacked a proper wind tunnel, so the team improvised. Using a high-pressure compressor designed for jet startup systems, they constructed a crude airflow rig from plumbing pipes and glass panels. The test models were suspended on fine wires, illuminated by desk lamps scavenged from offices, and filmed with 16mm cameras at 200 frames per second. In these flickering images, von Ohain saw the first proof of his theory. At 35-degree sweep, air separation along the leading edge decreased visibly. The flow stayed attached longer, the vortices softened, and drag fell by nearly 18% at simulated speeds of 800 km/h. The data was compelling but dangerous. Officially, Heinkel had no authorization for aerodynamic experiments outside government directives. The Luftwaffe's technical office, Reichsluftfahrtministerium, had dismissed the swept-wing concept as a theoretical curiosity with no practical wartime value. Their priority was production volume, not new physics. Each day spent on theory meant fewer jets delivered to the front. Von Ohain's reports had to be disguised as engine flow efficiency tests to secure access to lab equipment. Meanwhile, the contrast with Allied development was striking. Across the Channel, the British Gloucester Meteor entered service in July 1944 with conventional straight wings reliable, but limited to around 670 km/h. The Americans' Bell P-59 era Comet was even slower. Both programs prioritized simplicity over speed. Germany's Me-262 was faster but at the edge of control. In a silent corner of war-torn Europe, von Ohain's small team was about to cross that edge. Each experiment brought new failures. On one test run, the model's wing root collapsed under airflow pressure, sending fragments across the workshop. Another time, a high-speed test caused the compressor to explode, shattering its glass housing and nearly killing a technician. But amid the wreckage, they found valuable data. The failures revealed where the structure needed reinforcement and where airflow compression peaked. The equations that followed, scribbled in pencil across ration booklets, showed that drag coefficients dropped dramatically as the sweep angle increased beyond 30 degrees. Encouraged, von Ohain began translating his findings into a full-scale design. Project 1072, P-1072. It would be a twin-jet fighter powered by the HS-011A next-generation axial flow turbojet, producing 1,300 kilograms, 2,160 pounds of thrust per engine. The wing planform was set at a 35-degree sweep with a slight dihedral, a narrow fuselage, and a T-tail configuration to stabilize airflow at high angles of attack. His calculations suggested a theoretical top speed approaching 950 km/h, 590 mph, beyond anything then flying. Heinkel's senior engineers reacted with skepticism. The production directors, already strained by shortages, questioned why anyone would waste labor on unapproved prototypes. "We need engines, not fantasies," one supervisor muttered. Even Heinkel himself, though intrigued, warned von Ohain not to expect official support. The war economy had no patience for ideas without immediate results. Still, a few colleagues secretly admired his persistence. One recalled, "He never raised his voice. He only drew calculated and redrew. The rest of us chased deadlines. He chased principles." Late at night, when the factory lights dimmed for blackout, von Ohain and his team continued working by lantern glow, measuring air pressure with salvaged barometers and charting flow lines by hand. By early 1944, they had refined their model to near perfection. The small prototype, barely the length of a fighter's wingtip, produced data that confirmed what wind tunnel tests in Göttingen had hinted a decade earlier. The swept wing could maintain lift and stability beyond Mach 0.8 without structural failure. But these were numbers on paper. The challenge now was to prove it in flight. Von Ohain submitted his findings to the Air Ministry's Aerodynamics Board in February 1944. The committee's response was blunt. Not a priority. Experimental only. His reports were filed and forgotten. Yet within Heinkel's walls, plans for a test airframe continued in secret. Drawings labeled Experimental Stability Project disguised what was, in truth, the blueprint for the world's first true transonic aircraft. The odds were impossible. Germany was losing the war, its factories shattered and fuel reserves drained. But for von Ohain and his handful of technicians, this was no longer about victory, it was about validation. They believed that the principles they had uncovered would outlive the conflict. By the spring of 1944, as Allied bombers darkened the skies over northern Germany, the first components of the P-72 were being assembled in a shuttered hangar at Marianne. Aluminum ribs were fitted with precision hand tools. Wooden templates shaped the curved sweep that would one day define the future of flight. The transformation had begun quietly, born not of orders or ideology, but of a physicist's refusal to accept the limits of air. By early 1945, the first prototypes were ready, not officially approved, but ready enough to risk lives on. The first real test came on February 12, 1945, at Marianne Airfield, along the frozen Baltic coast of northern Germany. The war was collapsing on every front. Soviet artillery could already be heard on distant nights, and Allied bombers darkened the skies each morning. Yet inside a secluded hangar, behind tarpaulin-covered scaffolds, one final act of defiance was being prepared. The prototype bore no markings of the Reich, no swastika, no production code, just a penciled label on its fuselage. P-72. The aircraft stood unlike anything before it. Its swept wings angled backward at 35 degrees, narrow and sharp as blades. The twin HES-011 turbojet Siege, capable of over 1,300 kilograms of thrust, were mounted low beneath the fuselage, their intake cones hand-polished to reduce turbulence. The nose was long and pointed, designed to cut shock waves rather than push them aside. Around it, mechanics in worn leather coats checked fuel lines and ignition relays under the dim light of hurricane lamps. The floor glistened with a thin sheet of ice. The man who would fly it was Erich Varsitz, a test pilot already famous within Heinkel for taking risks no regulation allowed. He had flown the world's first rocket-powered plane, the He-176, in 1939. Now, 6 years later, he faced an even stranger challenge, a jet, whose stability no one could predict. Officially, the test did not exist. No Luftwaffe order authorized it. There would be no cameras, no documentation, and no report to Berlin. At 07:40 hours, the engine started. The first ignition failed. The second caught violently, expelling a jet of blue flame that lit the hangar walls. Ground crews winced as the turbines shrieked to full rotation, their pitch rising past human comfort. The airfield temperature was below freezing, and the fuelan experimental mixture of kerosene and benzene burned unevenly. The P-72 shuddered but held together. Varsitz taxied slowly toward the snow-dusted runway, the aircraft's nose dipping slightly as the front strut compressed. He paused at the threshold, engines idling at 30% power. Mechanics stood at a safe distance, faces wrapped in scarves, unsure whether they were watching an experiment or an execution. Then, without radio clearance or tower acknowledgement, Varsitz advanced the throttles. The jet surged forward. Its twin exhausts left twin scars of flame across the frozen airstrip. Within seconds, it reached 200 kilometers per hour, 124 milliliter, then 300. After 20 seconds, the lift overcame drag, and the P-72 left the ground. The flight was real. Observers described the takeoff as smooth but unnerving. The swept wings, far narrower than the Mi-262's, seemed to cut the air in silence. At 500 kilometers per hour, the aircraft leveled. At 700, it climbed. Ground instruments recorded data that made no sense at first. Minimal pitch oscillation, reduced vibration, and almost no sign of the abrupt nose tuck that plagued the Mi-262. The new wing geometry was working. At altitude, Warsitz reported over the short-range transmitter, "Engines unstable, but airframe steady." The phrase, later copied into maintenance logs, became the first confirmation that von Ohain's crazy theory had achieved flight stability. For 10 minutes, the aircraft circled above the Baltic coastline, maintaining speeds between 780 and 820 kilometers per hour, 485-510 mph, dangerous territory for conventional designs. The wings absorbed airflow that would have torn standard jets apart. Ground observers, using theodolites and stopwatches, recorded the motion with disbelief. One mechanic later wrote in his diary, "It flew straight as a rifle shot. No dip, no twist, only the sound of air cutting itself in two." Inside the cockpit, however, the situation was far from serene. The left engine surged repeatedly, fluctuating between idle and maximum thrust. At these speeds, even minor imbalance threatened catastrophe. Warsitz throttled back, maintaining altitude with the right engine alone. As fuel ran low after 11 minutes, he began a cautious descent. Landing a jet was always hazardous. Landing one no one believed should exist bordered on impossible. At 250 kilometers per hour, 155 mph, the nose gear refused to extend fully. The hydraulic system, built from salvaged parts, froze under the cold. The plane touched down unevenly, skidding across the snow and shearing the right landing strut. The fuselage slid for nearly 150 meters, 500 feet, before stopping. The right wingtip broke. The left engine caught fire briefly before extinguishing itself in the snow. Silence followed. Mechanics rushed forward, expecting the worst. When they reached the cockpit, Warsitz was already climbing out, face streaked with frost, his flight gloves stiff with cold. "It works," he said simply. Those two words, according to later accounts, were all that mattered. The data from the flight was preserved by miracle. The onboard recording instruments, 3 barographs, and 2 gyroscopic sensors survived the crash intact. Their readouts showed something extraordinary. The swept wing reduced drag and pitch instability by roughly 30% compared to previous Heinkel configurations. Airflow separation, the bane of high-speed flight, was delayed until nearly Mach 0.85 threshold, once considered unreachable by subsonic aircraft. The test was classified immediately. Only a handful of engineers at Heinkel knew of its success. Copies of the data were hidden in coded project folders labeled Engine Stress Evaluation to avoid discovery during inspections. The Reich's leadership, obsessed with jet production numbers, never heard of the P-1072 flight. Within weeks, Allied bombers destroyed large portions of the Maria Nehe facility. But the documents and von Ohain's handwritten notes were smuggled out by train to Heinkel's underground storage at Schwechat near Vienna. Meanwhile, Allied aerial reconnaissance photographed the site days after the test. Intelligence officers noted a new swept-wing shape under construction, but analysts in London dismissed it as a decoy or misidentified rocket glider. The true significance of what they saw would not be understood for another 2 years. For the men who witnessed the flight, it was a moment suspended between triumph and futility. They had proved the impossible, but at a time when proving anything could no longer change the outcome of the war. Von Ohain's name did not appear on any report. Warsitz's flight record was never logged in official archives. To the world, the P-1072 never existed. And yet, buried beneath snow and debris, the fragments of that prototype contained a new truth about the future of flight. The swept-wing design, dismissed as a theoretical curiosity, had just crossed the boundary between imagination and reality. By dawn, it was clear the field hack had saved lives, but no one dared put it in writing. Word spread fast through the maintenance bays and drafting rooms of a dying Reich. The winter of 1945 was collapsing into chaos, yet inside the remnants of Germany's aviation network, whispers of an impossible flight began circulating. Engineers from Junkers, Messerschmitt, and Focke-Wulfmann, accustomed to strict hierarchies, and endless forms spoke quietly of a Heinkel prototype that had flown faster and truer than anything before it. No official reports existed, only rumor, fragments of diagrams, and the testimony of a few surviving mechanics. Still, the idea had escaped the hangar. The news reached the Junkers Design Bureau in Dessau first, carried by a displaced technician from Marianne. He had seen the strange aircraft with his own eyes. Swept wings, smaller control surfaces, no external reinforcement. Junkers aerodynamicist Hans von Ohain, who was then developing the TA-183 Huckebein, immediately recognized its significance. His own sketches already featured a 40-degree sweep-up bold theoretical leap meant to overcome the same drag crisis that had haunted the Mi-262. When he learned that von Ohain's prototype had actually flown, he ordered his team to re-examine every wind tunnel model. The results confirmed what Heinkel's forbidden experiment had hinted. Swept wings did not merely improve stability, they redefined the limits of flight itself. Even as Allied forces advanced across Germany, technical cross-pollination among aircraft firms accelerated. Desperation bred cooperation. Messerschmitt engineers, working on late-war jet projects like the P-1101, quietly borrowed concepts from Heinkel's design notes. The Mi P-1101 was intended to have variable sweep wings, a mechanism allowing adjustment between 35 and 45 degrees, depending on speed. Though the war ended before its completion, its design was a direct echo of Ohain's work. These projects, half-finished and scattered across underground bunkers, would later become treasure maps for post-war aviation. When Soviet troops captured Marianne Airfield in April 1945, they found wreckage scattered among frozen craters. Among the debris were fragments of unfamiliar wings, thin, sharply angled, and riveted unlike any aircraft in known production. Soviet engineers, trained at the Central Aerohydrodynamic Institute, TSAGI, immediately understood what they were looking at. The fragments were shipped to Moscow under guard. Soviet scientists later confirmed. The sweep angles matched aerodynamic research conducted. In Germany, as early as 1943, these remains would influence early MiG jet development within just a few years. Meanwhile, the Western Allies were already hunting for similar secrets. The U.S. Army Air Forces formed a special unit, Watson's Wizards, tasked with locating and seizing advanced Luftwaffe technology before it could fall into Soviet hands. Their teams swept across Bavaria and northern Germany, cataloging every document, airframe, and surviving engineer they could find. In early May 1945, they reached the Heinkel Works in Schwechat. Among stacks of burned files and twisted fuselage sections, they recovered drawings labeled P-272 High-Speed Aerodynamics Study. The notes were signed simply H. V. Ohain. The documents were flown to Wright Field in Ohio for analysis. There, engineers at the U.S. Army Air Technical Intelligence Division began comparing the swept wing diagrams to their own straight-wing prototypes. Early wind tunnel simulations indicated that a 35-degree sweep could increase critical Mach number by as much as 0.08, translating to roughly a 20–25% gain in top speed without major structural reinforcement. The discovery caused a quiet revolution. The Americans had found a key to surpassing the limits of propeller-driven flight. In the months that followed, von Ohain's once-secret geometry began appearing in classified design reviews across the Allied aviation industry. At North American Aviation, engineers developing a new fighter concept later known as the F-86 Sabre adopted a 35-degree wing sweep almost identical to the Heinkel data. In Britain, aerodynamicist W.E.W. Petter at English Electric proposed a similar sweep for future high-speed jets. The Soviets, working with fragments from the Ta-183 and Marianne prototypes, would soon create the MiG-15, whose 35-degree wing sweep and performance characteristics mirrored the same German lineage. Inside Wright Field's secret hangars, the phrase "the German madness that worked" became an inside joke among American engineers. They could hardly believe that the concept, dismissed as lunacy by the Reich, was now reshaping their own designs. Data from the captured Heinkel reports showed a direct comparison. While the Me-260 maxed out at 870 km per hour, 540 mph, before instability, the projected swept-wing design could theoretically exceed 950 km/h, 590 km/h at level flight. This performance advantage was too significant to ignore. Still, acceptance was not immediate. Many test pilots distrusted the new geometry, claiming it would cause unpredictable stalls and dangerous spins. The Bell Aircraft Company, running trials with experimental swept-wing models, lost one prototype during testing when control was lost at high angle of attack. Engineers called the new configurations death traps, until mathematical modeling and later, real data proved their inherent stability at transonic speeds. Slowly, confidence grew. As Allied engineers debated and recalibrated, German scientists who had survived the war were being quietly absorbed into post-war programs under Operation Paperclip and its Soviet counterpart. Von Ohain himself, captured by American forces in 1945, was interviewed at length about his research but remained understated. He offered no grand claims, only explanations grounded in physics. One report noted, "Subject displays no ego, only conviction that his theory is correct." By 1946, the influence of the swept-wing concept had become undeniable. Both superpowers were independently constructing aircraft using angles derived directly from German blueprints. What began as scattered fragments of data hidden in crates, smuggled out of bombed hangars, or translated from half-burned notebooks was now fueling a global race into the jet age. The irony was complete. The idea dismissed by the Reich's bureaucracy as impractical now underpinned the very machines that would dominate the skies for the next half-century. Von Ohain's once forbidden innovation had transcended defeat, surviving not through politics or propaganda, but through pure engineering logic. By the end of 1946, test pilots in both East and West were flying swept-wing prototypes without realizing their shared ancestry. The crazy German design had crossed borders, ideologies, and continents not through espionage or secrecy, but through the unstoppable momentum of truth in physics. By 1947, the quiet modification had turned into an open secret even high command couldn't ignore. Eventually, proof arrived not in theory but in numbers. By 1947, 2 years after the end of the war, engineers in the United States and the Soviet Union were racing to master the mysteries of high-speed flight. Both nations possessed fragments of the same secret: German swept-wing research, recovered from bombed laboratories and hidden airfields. At Wright-Patterson Air Force Base, Ohio, a classified report titled "Evaluation of German Swept-Wing Aerodynamics" began circulating among senior engineers. Inside its pages were calculations that seemed to defy the established laws of aerodynamics. The data, traced back to Heinkel's Project 1072 and Messerschmitt's P1101, showed that sweeping the wings backward could delay the onset of drag near Mach 1 by a full tenth of the speed of sound. The numbers were staggering. Conventional straight-wing jets began to experience severe drag rise and control loss at Mach 0.78, roughly 600 mRMP at high altitude. But the Heinkel data demonstrated that a 35-degree wing sweep could push that barrier to Mach 0.88, or about 675 meters, 1,085 km/h, without catastrophic instability. For the first time, engineers could quantify what wartime witnesses had only observed. The swept wing was the key to surviving transonic flight. To confirm it, the U.S. Air Technical Intelligence Command constructed a new test program. Engineers mounted captured German wings to experimental aircraft and ran wind tunnel trials at Langley Field, Virginia. Among the scientists involved was Robert T. Jones, whose independent theoretical work at NACA had reached similar conclusions. The Heinkel data provided the missing empirical proof. The swept-back wing, Jones wrote, delays the critical Mach number by a measurable and repeatable amount. The concept was no longer theoretical, it was verified. Captured engineers were summoned to Wright-Patterson for debriefings. Hans Multhaup designer of the Ta-183, and Hans von Ohain, the quiet physicist who had started the revolution, were among them. The transcripts of their interviews reveal a mixture of technical precision and humility. When asked about the purpose of the swept-wing configuration, von Ohain replied, "It was the only way to make air behave at those speeds." His phrasing was simple, his tone matter-of-fact. To the Americans listening, it was as though the riddle of high-speed flight had been solved by a man who had never sought glory. The effect of these discoveries rippled through the Western aviation industry almost instantly. At North American Aviation, Chief Engineer Edgar Schmood ordered his design team to incorporate a 35-degree sweep into their next-generation fighter, originally conceived as a straight-wing aircraft. The result was the F-86 Sabre, first flown in 1947. In parallel, the Bell Aircraft Corporation, responsible for breaking the sound barrier with the rocket-powered X-1, began to adopt similar aerodynamic shaping in later jet designs. Across the Atlantic, British engineers at de Havilland and English Electric quietly did the same. Testing confirmed the difference. At 30,000 feet, the straight-wing FJ-1 Fury, the Sabre's predecessors, struggled to exceed 880 km/h, 550 mph. The F-86, with its swept-wing geometry, achieved 1,000 km/h, 620 mph in level flight. At those speeds, the reduction in drag was measurable. Lift-to-drag ratios improved by 14%, roll stability increased, and control response remained predictable even as the aircraft approached the transonic range. What had once been a crazy idea in a German hangar was now a benchmark of Allied engineering. By the late 1940s, similar breakthroughs were occurring behind the Iron Curtain. In Moscow, engineers at the Mikoyan-Gurevich Design Bureau, armed with German documents and fragments from the Ta-183, completed development of the MiG-15. Its wings, swept 35 degrees, bore a near-identical profile to the Heinkel P-1072. When it first flew in 1948, its performance stunned Western observers. A top speed exceeding 1,075 km/h, 668 mph, and combat ceilings unmatched by any Allied aircraft. Neither side admitted it then, but both superpowers were flying on the same aerodynamic inheritance. The ultimate proof came not in laboratories, but in battle. When the Korean War erupted in 1950, the world witnessed the first jet-versus-jet combat in history. On one side stood the Soviet-designed MiG-15, on the other, the American F-86 Sabre. The two aircraft descendants of the same German theories faced each other over the Yalu River in hundreds of engagements. Reports from U.S. Air Force pilots revealed a stark truth. At high altitude, the Sabre's swept-wing design allowed superior roll control and smoother recovery in dives. Statistical summaries from 1953 showed a 10.1 kill ratio in favor of the F-86 during sustained combat. The shape of its wings, the same 35-degree sweep born in wartime secrecy, was the silent advantage. Meanwhile, within Wright-Patterson's archives, the technical reports mounted. One evaluation concluded, German aerodynamic research in swept-wing design represents a decisive step in overcoming compressibility limitations. The conclusion was unambiguous. What the Reich had abandoned as impractical had become the cornerstone of the jet age. By 1952, the legacy of von Ohain's work was formally acknowledged. Now working for the U.S. Air Force Research Laboratory, he contributed to the development of advanced propulsion systems, applying the same disciplined logic that had once guided his forbidden experiments. He was awarded the AIA's Goddard Award years later for contributions to jet propulsion theory, though he rarely spoke of the P-1072 again. Colleagues described him as precise, detached, and endlessly curious. When asked about recognition, he replied, "The proof is in the air itself." There was irony in that proof. The Heinkel data that had been dismissed by the Reich Air Ministry in 1944 as irrelevant theory had become the foundation of Western air power. Allied engineers credited the captured documents in internal memos, though public acknowledgement was muted. Official history spoke of independent rediscovery rather than direct inheritance, but those who handled the documents knew better. One engineer at Wright Field later wrote privately, "The jet age did not begin in Dayton or Moscow, it began in the ruins of Maria Nehe." By the close of the decade, the swept-wing principle was no longer a curiosity. It was standard practice. Every major jet, the F-100 Super Sabre, the Hawker Hunter, the MiG-15, and even the early Boeing 707 carried the same geometric signature. The drag curves first plotted by von Ohain and his team now appeared in every aerodynamics textbook. For historians of flight, the path from secrecy to supremacy was clear. What began as a desperate wartime improvisation, tested in freezing air over the Baltic, had redefined the limits of the possible. The idea had crossed nations, ideologies, and wars without fanfare, carried not by propaganda but by physics. By the early 1950s, no one could deny it. The swept-wing jet had become the emblem of the modern age. By the war's end, even enemy engineers quietly admitted what the data had long proved. In the years that followed, the world's skies filled with echoes of one man's crazy idea. By the mid-1950s, the swept-wing once dismissed in Germany as a theoretical indulgence had become the defining feature of the modern jet age. Every major air force, every aircraft manufacturer, and every nation chasing the promise of speed now relied on the same elegant backward angle first penciled onto scrap metal in 1943. From the F-86 Sabre that ruled the Korean skies to the MiG-15 that challenged it, from Britain's Hawker Hunter to the emerging Boeing 707 passenger jet, the shape of the future had been forged in the collapse of the past. Hans Joachim Pabst von Ohain never sought fame for it. In 1947, under Operation Paperclip, he was quietly relocated to the United States along with dozens of other German engineers. He joined the U.S. Air Force Research Laboratory at Wright-Patterson Air Base, the same place where his confiscated wartime notes had once been studied in secrecy. There he worked not as a celebrity scientist, but as a measured, precise researcher. His focus shifted from aerodynamics to turbojet efficiency and combustion stability, where his understanding of airflow once again guided breakthroughs. For decades he wrote papers, trained young engineers, and insisted that innovation came not from boldness, but from careful reasoning under constraint. The broader world, however, had already absorbed his unspoken influence. By the 1960s, the swept wing was standard across nearly every high-speed aircraft, military and civilian alike. The MiG-21, the F-104 Starfighter, and the English Electric Lightning all carried the same backward geometry. On the civilian side, the Boeing 707 and Douglas DC-8, the first true jet airliners, adopted the sweep to balance efficiency and speed at cruising altitudes near Mach 0.8. Even as engines became more powerful and materials advanced, the fundamental aerodynamic logic remained unchanged. A backward-angled wing moved the critical drag rise further out, granting smoother flight and lower fuel consumption. The lesson was simple and permanent: nature could be persuaded, not forced. For von Ohain, recognition came late. His wartime experiments had remained classified until the late 1970s, and his name was often overshadowed by more publicized figures like Sir Frank Whittle, Britain's pioneer of the turbojet. It was not until the 1990s, when declassified Allied reports from Wright-Patterson and Langley were released, that historians began piecing together the chain of influence leading back to Heinkel's secret hangars. Among the most striking documents was a 1947 report explicitly crediting data recovered from Peplatron for advancing American aerodynamic modeling. NASA. Historian Dr. Richard Hallion later summarized it succinctly: without the Heinkel data, the jet age might have come a decade later. The statement was more than praise. It was acknowledgement that the most transformative leap in post-war flight had originated not from a superpower's research budget, but from a desperate wartime improvisation carried out by 5 men under candlelight. By the time his contributions were fully recognized, von Ohain was already retired. He lectured at the University of Dayton, where students recalled him as calm and meticulous, with a quiet voice that carried authority through precision rather than volume. When asked about his wartime work, he would smile politely and redirect the conversation to physics. "The war was noise," he once said. "The air was what mattered." Meanwhile, the technological lineage he began continued to evolve beyond his lifetime. The F-4 Phantom II, F-15 Eagle, and even the F-22 Raptor, separated by half a century each, owed their aerodynamic stability to the same basic principles refined in 1944. Advances in materials, control systems, and fly-by-wire computing refined the concept, but the foundation never changed. The sweep angle, the distribution of lift, the management of compressibility, all still echoed the patterns drawn on von Ohain's scrap metal sketches. Beyond fighters and bombers, the principle shaped commercial flight itself. The wide-bodied jets that connected continents in the late 20th century, Saturn 47s, A300s, and traced their efficiency to the same understanding of airflow that had once saved a prototype from crashing into the Baltic. Even in spaceflight, delta-winged orbiters like the Space Shuttle Incorporated swept geometry to balance re-entry drag and thermal loads. The curve of progress, traced through the shape of a wing, pointed directly back to the winter of 1944. Von Ohain never sought to profit from his innovation. He lived modestly, publishing technical papers and avoiding the public spotlight. When he received the AIAA Goddard Award for Outstanding Contributions to Propulsion, he reportedly remarked only that, "The air still holds more secrets." To colleagues, he represented the ideal engineer driven not by ambition, but by curiosity. His humility mirrored the quiet precision that had defined his life's work. As historians reassessed the wartime era, a deeper pattern emerged. Nearly every major technological leap in aviation, from radar to jet propulsion, had depended not on official directives, but on individuals willing to think beyond orders. Von Ohain's story became a symbol of that tension between obedience and imagination. Under the strictest and most oppressive system of control, he had found freedom in mathematics. His innovation did not win a war, but it redefined what came after. In retrospect, the legacy of the swept-wing jet stands as both a triumph of science and a parable of circumstance. It proved that even in the darkest conditions, clarity of thought could survive bureaucracy, ideology, and defeat. The men who once called the design madness lived to see their own countries adopt it. The nation that abandoned the idea became the blueprint supplier for its former enemies, and the physicist who refused to stop drawing under candlelight helped humanity cross into the supersonic frontier. When von Ohain died in 1998, obituaries were brief but respectful. They called him a pioneer of jet propulsion and one of the founding minds of the modern age of flight. Few mentioned the P-1072 or the winter in which it flew. Yet for every pilot who lifted off in a swept-wing aircraft, his influence lingered invisibly in the air. In the measured calm of post-war reflection, his story stands as a reminder. Innovation rarely announces itself with fanfare. It begins quietly, often in defiance, often in failure, and endures because the laws of nature cannot be silenced by authority. War rewards survival, but it's the quiet thinkers who keep it possible.